Let's just do a ton of more examples just so that we make sure that we're getting this trig function thing down well. So let's construct ourselves some right triangles. Let's construct ourselves some right triangles. And I want to be very clear. The way I've defined it so far, this will only work in right triangles. So if you're trying to find the trig functions of angles that aren't part of right triangles, we're going to see that we're going to have to construct right triangles. But let's just focus on the right triangles for now. So let's say that I have a triangle where, let's say this length down here is 7. And let's say the length of this side up here, let's say that that is 4. And let's figure out what the hypotenuse over here is going to be. So we know, let's call the hypotenuse h. We know that h squared is going to be equal to 7 squared plus 4 squared. We know that from the Pythagorean theorem, that the hypotenuse squared is equal to the square of each of the sum of the squares of the other two sides. H squared is equal to 7 squared plus 4 squared. So this is equal to 49 plus 16. 49 plus 16. Let's see, 49 plus 10 is 59. Plus 6 is 65. It is 65. So this h squared, let me write h squared. It's a different shade of yellow. So we have h squared is equal to 65. Did I do that right? 49 plus 10 is 59, plus another 6 is 65. Or we could say that h is equal to, if we take the square root of both sides, square root of 65. And we really can't simplify this at all. This is 13. This is the same thing as 13 times 5. Both of those are not perfect squares, and they're both prime, so you can't simplify this anymore. So this is equal to the square root of 65. Now let's find the trig. Let's find the trig functions for this angle up here. Let's call that angle up there theta. So whenever you do it, you always want to write down, at least for me it works out to write down. So